Good evening, everyone. My name is Yusuf Fathi, and today I'll be presenting to you the paper Decision Transformer Reinforcement Learning via Sequence Modeling. The outline will go as follows. The method we're presenting today is called Precision Transformer, and this method is proposing a complete replacement for conventional RL algorithms. It combines concepts from supervised, model-free offline RL and using sequence modeling in order to come up with an algorithm that performs at par or even sometimes better than the state-of-the-art RL algorithms from the same domains. So before going into how this method actually works, we need to present some preliminary knowledge that would help us understand the methodology of this paper a bit more. To begin with, most reinforcement learning algorithms are modeled as a Markov decision process, short for an MDP. And for the two main categories of our algorithms, which are model-based and model-free, we have different MDPs as shown here. So you can see for the model-based, we have states, actions, a known transition model between states, a known reward model for state action pairs, discount factor, and a horizon H. However, for model-free algorithms, we can see that the transition model and the reward model are now completely unknown. And this is why these methods are considered much more challenging and require different RL approaches than the model-based ones. In the most traditional model-free RL settings, we assume that we have an agent, and this agent interacts with the environment by doing specific actions and receives feedback from the environment in the form of rewards and states. This process is called online RL, as the agent is in continuous interaction with the environment by generating state action reward tuples until a stopping condition is reached at the end. The target of such methods is to maximize the expected sum of discounted rewards, and these rewards are actually discounted to account for the convergence of such methods. One very famous way to do that would be to assume that we have a Q-value function, which estimates the expected rewards we'll get by being at state S, doing action A, and continuing with the current policy till the end of the trajectory. These methods basically rely on concepts called temporal difference and Bellman backups, which is shown here in this equation to optimize this value function, and they rely on the policy that we currently have, which chooses the best action to do given a specific state. For some environments, this can be quite challenging due to the high cost and high risk that we have for interacting with these environments, which happens in robot control tasks, for example. Another big challenge is the credit assignment problem, which happens due to the discounting in the Bellman backups. I would like to quickly go through the credit assignment problem by explaining the key-to-door environment. In this environment, we assume that the agent goes through three phases. In the first phase, the agent is placed in a room with a key in it and has the option to either take that key or not. Then the agent is moved to, in the second phase, to another room where there is nothing in it, and this is basically called the distraction phase. And then the agent is moved to a third room in the third phase where there is a door in there. And the agent only gets a reward if they reach the door in the third phase and had already taken the key in the first phase too. This is quite challenging because we need a way to propagate the final reward that the agent takes in the final phase to the action that they did at the start of the trajectory in the first phase, while actually ignoring all of these distracting states and actions that were done in the second phase. A possible solution in the literature would be associating the reward we get with specific important state with something called state association. But in general, this problem still remains quite challenging for most RL algorithms that are existing out there. Current line of approaches are called offline RL algorithms, and these methods solve the high cost and risk of interaction with the environment by assuming that we only learn from a fixed dataset that requires no further interactions with the environment by any means. This means that our trajectories now are already pre-generated with a specific length, and one of the popular methods to do that is called the DTPG method. A main challenge in these approaches is the distribution shift or extrapolation error. And to explain that, let's look at the temporal difference equation that we showed previously. And if our policy is choosing the action that gives us the maximum reward given the current state S prime, then what if this policy chooses a rarely visited state action pair? The Q value will then give us, the Q function will give us inaccurate estimate of the expected rewards, and this inaccuracy and error will propagate with us till the end, leading to the low and bad performance of the method. Solutions were proposed to solve this, and one way is to constrain the policy action space by choosing only actions that we've seen before in the dataset a few times, Another way is to incorporate value pessimism by including a lower bound on the value function in order to avoid the overestimation that happens when an error occurs. Another different domain of RL is called supervised RL. And in these methods, we allow the agents to train using supervised losses. One way to do that is by imitation learning. And in these methods, we try to imitate the behavior that was observed in existing trajectories shown to the agent. And a basic version to do that is called behavioral cloning. And these methods actually assume that we have function f that maps the states to actions with no regards to rewards whatsoever by using supervised losses, of course. The drawbacks of such methods is that what if we give this function f a new state that we have seen in the real world and it has never seen before? Then we would probably it will not be able to generalize to these new scenarios and it will give unpredictable outcomes. It also requires a very large amount of optimal and expert observations, which might be hard to get in some environments. And lastly, we assume that the states and action pairs are independent and identically distributed, which is not necessarily the case. Another very recent line of approach is trying to shift the perspective on how do we approach RL problems in order to solve the issues that we see in deep RL algorithms or re-imitation learning. So the target now is, instead of training agents to maximize the rewards, we are training agents to follow the commands such as obtain so much total reward in so much time. In other words, we are allowing the agent to use suboptimal trajectories and conditioning on the and through conditioning on the target returns of those trajectories, the agents should learn how to generate the actions in those trajectories that would give the target return that it was conditioned on at the beginning. Specifically, given the Q-value function, which takes the observation and action to return the value we expected return, we will change that in an upside-down way and generate something new, which is called the behavior function. This behavior function takes the observation and a command in the form of a desired return or a desired horizon, and the function will give us the action that should be done in order to get this desired return at the end. This method will be optimized in a supervised way by using a supervised loss between the action that the behavior function produces and the action that it should have got from the trajectory that already exists. There are several variants for that. Some methods learn by conditioning on rewards, others reward by conditioning on states. However, most of these methods, as promising as they are, they still have a huge gap between the state-of-the-art RL algorithms. However, they're extremely promising since the agents could have the ability to extrapolate beyond what it sees, and they could be queried and conditioned on larger returns that they have seen in the existing dataset, and they can generate new sequences that could give us those states as an output. We've said at the beginning that decision transformer method is using sequence modeling. And to explain that, we need to go through a concept that was introduced in the NLP domain called attention. In general, given two sequences, we would like to learn a representation for the specific words in these sentences that depends on the context in which these words appear in the sentence. For example, in the first sentence, we want to learn a context representation for the word it that depends mainly on the word cat. However, in the second sentence, we want to learn a different representation of the word it that actually depends on the word milk more. So we want to focus more on cat in the first sentence and on the word milk in the second sentence to get different context representations for the same word, which is it. The way attention works is that given a word that we want to learn the context-based representation for, such as the word it in the previous example, we learn a query representation. And for all other words in the sentence, we learn a key representation and a value representation for them. What we do is that we do a dot product between this query and all the other keys to get similarity vectors. And then we do a softmax between all of these similarity vectors to make sure that they all sum to 1. We then multiply these similarity vectors by their corresponding values, and we sum them all up to get the final context-based representation for this query word that is mainly based on the similarity between all the other words in the sentence. But what is sequence modeling, and what types of model architectures that were able to do this task successfully? Sequence modeling is about predicting an input sequence from a corresponding input set of values. Examples for tasks involving sequence modeling are machine translation, for example. And existing models that were able to do this task successfully are known as recurrent neural networks, and examples for them are LSTMs and GRUs. However, quite recently, there has been a very powerful architecture that emerged, which is called the Transformers architecture. This architecture showed very powerful generalization abilities while being able to solve the vanishing gradient problem that was persistent in the existing RNN architectures. It also allowed for very accurate modeling of long-term dependencies. But how does it work specifically? So as we see here, it takes as an input an input sequence of tokens, and then these tokens are embedded with a positional encoding to give a notion of their locations. These are then passed to a multi-headed attention layer, and we show here in the right that this mainly carries out the attention mechanism that we explained in the previous slide, while using the concepts of keys and values and query representations. The output is then passed to a feed-forward network to give the final context-based representation of each input sequence element. Now comes the output sequence, and we pass the output elements that we generated so far to the same multi-headed attention layer to get a context-based representation for them. Then we do cross-attention to get the context, but based on both the encoded inputs and the encoded outputs so far. We then pass that to a final linear layer that predicts the next output sequence element. And we keep on doing that until the output sequence generation is done. Transformers have generally been used in the field of reinforcement learning to enhance the performance of existing tasks that rely on sequences, such as partially observable RL algorithms and imitation learning. However, they were still in most cases combined with traditional RL algorithms. So this is the first time in this paper to use transformers with sequence modeling in the context of upside-down RL without relying on any traditional RL concept. One important detail to note here is that for the original Transformers architecture, in order to generate a context-based representation for one word, we need to use the words that are occurring before the word and after it. However, for the GPT variant Transformer architecture, it only assumes that we have access to the sequence elements that were generated so far, and we have no access to the future sequences. Therefore, the word mainly is based on, or the context of the word is based on the words that are before it, not after it. Now we explain the exact architecture of the decision transformer model. Based on what we saw in the background knowledge, the decision transformer architecture actually uses the concepts from upside down RL, and it's specifically very similar to the method by Kumar et al., with some differences that we will highlight in a bit. It is a model-free offline architecture that uses sequence modeling using the GPT transformer, and the method shows that it can solve the credit assignment problem implicitly, has no distribution or distribution shift or extrapolation error, requires no expert demonstrations, and the evaluation shows that the results match or even exceed some of the state-of-the-art model-free offline traditional RL algorithms. But how do they do that? Let's start by the input setup. Similar to upside down RL, we would like now to change the perspective. So instead of maximizing the sum of rewards, we now want to condition a behavior function on the target return that we want and predict the action that should be done. In order to do that, we take the original representation of the trajectories in an offline dataset and we transform it to an alternative representation, where we basically replace each reward item with the rewards to go, which is basically the summation of the rewards from the current time step till the end of the episode. And this is the new trajectory representation that is used in the training pipeline of our model. So how do we actually train our model? We start with taking a subsequence from the existing trajectories, which has a context length of k, and we call these input tokens. We then pass each token type to a unique linear encoder that gives us an embedding for each token, and we also add to them a time embedding that gives the model a notion of the time step for each of these tokens. We pass all of these embeddings to the GPT transformer. And as we said in the background, the GPT transformer would give us a contextualized representation for each of these input tokens that is mainly predicted based on the previous tokens and not the future ones. In this model, we're mainly concerned with the corresponding output representation for the state tokens. So we take them and we pass them through a linear decoder that gives us the final prediction of the actions that should be done at each time step. Depending on whether, if we're, for example, using discrete actions, we would supervise this architecture using cross-entropy loss. If we're using continuous action, we will supervise using mean squared error, for example. The main difference between this architecture and the famous upside-down RL method by Kumar et al. Is that they use a context length of 1 and they have no notion of sequence modeling or transformers, while here we use both of these. So far, we've seen how we've trained the model in an offline fashion. Now it's time to see how we can test the model by conditioning it on a specific required target return and predict the actions, interact with the environment, collect feedback from the environment, then pass this feedback to the model to predict newer actions. So we start off by having a required return and an initial state. We pass them to the same linear encoders and the time embeddings that we said previously. Then we pass these two tokens to the GPT transformer, which will give us a prediction of the first action that we need to do. Then this action is passed to the environment, so we execute that action in the environment, and we collect the feedback in the form of a new state and a new reward. We pass the action token that we predicted to the transformer. We prepare a new token for the returns to go that is basically the decrementation of the reward that we just received from the rewards that were in the previous step to give us a new returns to go token. We also use the new state token as an input, and we use all of these input tokens, and pass them to the GPT transformer to give us a prediction of the new action that we need to do. And we the environment again, collect newer states, newer rewards, calculate newer tokens, especially rewards to go tokens, pass them to the GPT transformer, and the whole history is passed to the GPT transformer, and this allows us to predict a newer action that should be done, and this continues until a stopping condition is reached at the end. So as you can see now, we have a model that was able to use suboptimal trajectories in the training. However, it was able to infer the correct actions to do in order to match a specific target return that we gave it at the beginning. And why is this particularly interesting? This is because we have no notion of any of the traditional RL concepts. Specifically, we have no Q-value function, which means that we have no distribution shift in the offline training. We also have no Bellman backups, we have no discounting or even temporal differences, and the credit assignment can actually be done in one step by giving higher attention to the important states and actions that cause a specific reward, even if such a reward is delayed. This approach is also very promising since the transformers have so far shown extraordinary generalization abilities. This means that this model will particularly have and learn a complex joint distribution for rewards, actions, and states, and generally won't be constrained to what it saw in the training dataset and will generalize beyond that. We will see more about that in the following discussion and evaluation. For completeness, I show the pseudocode taken as screenshots from the original paper for the training and evaluation of the decision transformer architecture. It is essentially exactly the same as we explained in the previous slides. However, it is important to note that for the evaluation, we always keep a context length of k steps only that enter the transformer at any particular time step. Now we go through the experiments that was done to evaluate the performance of the algorithm and the results reached. The first set of experiments done in this paper were on the Atari benchmark, and these are a set of discrete control tasks in the form of games, and the paper chooses a set of 4 games to evaluate on, which are the Breakout, Qbert, Pong, and Sequest. For all the games, they choose a context length of 30, however for the Pong, they choose a context length of 50. This benchmark is considered challenging since the states are considered visual inputs, so the state representation is a bit complex, and some games also include some kind of a long-term credit assignment. The baselines that they compare with are the CQL, which is, by the time of writing this paper, is the state-of-the-art model-free offline RL method, and it is an instantiation of temporal difference learning with value pessimism in order to solve the distribution shift problem that we mentioned previously. There's also the REM method, which is an offline RL method. There's QEDQN, which is a distribution RL method. And lastly, we have BC, short for behavioral cloning. And it is exactly as we said in the background. They map states to actions in a supervised manner, and they implement this baseline themselves. The datasets of all the games are basically a 1% of the replay buffer of a DQN method. So we should relatively expect this to the trajectories that we are trained on, we should expect them to have relatively high rewards and good performance. The other benchmark that they evaluate on is the D4RL benchmark. And these are a set of fine-grained continuous control tasks in the form of games. And these games are the Half Cheetah, Hopper, and Walker. They also add the Reacher game, which is not part of the benchmark. However, it is a goal condition task with some sparse rewards, so it has a different setting than the other three games. The dataset settings they evaluate on is firstly the medium one, which is basically 1 million time steps generated by a medium policy directly. And here by medium policy, you mean that it's performing with a 1/3 of a score of an expert policy. There's also the medium replay, which is basically the replay buffer of an agent that is performing with the performance of a medium policy. The other one, the last one, is the medium expert, which is basically the unionization of the trajectory generated by a medium policy and an expert policy at the same time. For the baselines, they compare with the CQL and BC as the previous benchmark. However, they add the Baer and Brock, which are model free RL algorithms, and the AWR, which is an offline RL algorithm. So before jumping into the results reached by this paper, we need to highlight that these numbers shown here are the scores reached when these games are played. And all of these scores are gamer normalized, which means that a score of 0 means that the game was played by a random policy, and a score of 100 means that this is a score reached when a professional expert is playing the game. So looking at the results now, we can see that the DT is the decision transformer method that we're explaining in this paper. And if we compare that to the CQL, which is the state-of-the-art model-free offline RL algorithm, we can see that on the breakout game, it is actually performing much better than the CQL method, but the standard deviation is considerably high. When it comes to the Sequest game, we can see that it's performing slightly better than the CQL method with a much lower standard deviation. When it comes to the QBERT, we can see that the DT is actually performing much worse than the CQL method, and in the Pong, it's actually performing slightly worse. Now, looking at the BC, we can see that the BC is actually, it's only doing behavioral cloning. However, it's doing much better than the QRDQN and the REM methods. And when it comes to the CQL and the DT, it's actually performing quite closely to the DT, and the CQL might be even outperforming it in some of the games too. So in general, the conclusion we can reach from these results on the Atari benchmark, we can see that the DT method, the performance of it, is not consistently better than the other baselines on all of the games. When it comes to the D4RL benchmark, we can see that the DT method is performing quite more consistently than what we saw in the Atari benchmark. Specifically, we can see that the DT method is either performing much better than the best performing models from the other baselines, or it is at least performing at par or quite close to the other methods. We can also see that the STD in all of the dataset settings and all of the games is much smaller than what we saw previously in the Atari benchmark. Now we go into a deeper discussion to further analyze the performance of the decision transformer network. So the first two questions that we want to ask ourselves about the decision transformer architecture is that, is it able to, for a large data set, to focus and clone a specific subset of the data that gives the target return that it's conditioned on at test time or not? Also, the other question is, for a small data set, is the decision transformer able to go beyond what it sees in the training data? So to assess that, the authors created a new baseline, and they call that the percentile behavior cloning. And this is basically doing normal behavior cloning. However, it is trained on the top X% of the training dataset trajectories based on or sorted by the episodic rewards. So as you can see here, the 10% BC means that we're doing the behavior cloning on the top 10% of the trajectories based on their episode rewards. So as you can see in the results here, we can see that the percentile behavior cloning is actually doing much better than the state-of-the-art model-free offline RL algorithm, the CQL here. And when it comes to the DT, you can see that's actually performing at par and very competitively with the percentile behavior cloning, which means that it has the ability to focus on the particular subset of the whole training data that gives the required target return. When it comes to the small dataset, which is the Atari benchmark here, you can actually see that the percentile behavior cloning is performing much worse than what we saw previously. And this is basically because it's only able to mimic or clone a very small sample from the dataset. However, when it comes to the DT, you can see that's actually performing quite good. This means that the DT has the ability to generalize beyond the existing subsets that it saw in the trajectories of the training data, and it can utilize the distribution of all of these trajectories, even the ones that are different from what it is conditioned on at test time. So this experiment mainly shows us the great generalization ability of the decision transformer architecture. I would like to see whether the model is actually able to understand the target returns that it's conditioned on at test time or not, and is it able to predict action sequences that give the required rewards. So to assess that, they gave the models different target returns, and they observed the accumulated returns by the model, which is denoted here by the blue line. And they compare that to the optimal desired returns that are denoted here by the green line. So in general, we can see that for all the games, the model shows high correlation between the accumulated rewards and the desired returns, showing its ability to follow the commands and generate sequences that follow the target returns that it was conditioned on. Additionally, they also wanted to see whether it's possible to give the model higher target returns than the maximum returns that it saw in the training set, which is denoted here by the yellow line. And in general, on most games, you can see that the model was able to give close accumulated returns to the desired returns beyond the yellow line, which shows the ability of the model to extrapolate and generalize to sequences that would satisfy a higher returns to go than what it saw in the whole training set. Another aspect that we want to look at is the impact of the context length on the performance of the decision transformer architecture. This would also help in motivating the contribution of this paper over the original upside down RL method by Kumar et al. So originally, such method would use a context length of 1, and when we set such a context length for the DT, we can see that the performance is now much worse on all of the games as shown here. This means that a larger context length allows the transformer to learn a more rich distribution over the possible states and actions and rewards, which enables better learning in general and improved training. One of the main contributions that was mentioned previously for the decision transformer network is that it's able to solve the long-term credit assignment problem effectively with the use of the transformers and the attention inside of them. To assess that, we return back to the key-to-door environment that was mentioned in the background, and we typically train our models on random trajectories. Some of these trajectories may succeed in getting a trajectory with a reward at the end, and some may not. And here we compare the methods with success rates that typically tell us by how much percentage does the method returns trajectories that succeed and gives a reward at the end or not. So as you can see, the percentage BC here is performing quite well since it's cloning mostly successful trajectories from the random trajectories. However, when it comes to the DT, it's actually training on on all of the random trajectories, and it's performing quite well. And if we compare it to the CQL, you can see that the CQL is actually performing very poorly. This is mainly because it's using temporal differences and Q values, and it's basically unable to propagate the Q values over the long horizons that are present in this problem. So far, we've seen that the model is capable of predicting actions in an accurate way. So in other words, it is a well-performing actor. However, we want to assess if the decision transformers can actually be accurate critiques in a sparse reward setting. And by critiques, you mean is it able to predict accurate expected returns or not? So we assess that in the key-to-door environment setting too. However, we change the setup a little bit. So the model now, instead of returning only action tokens, it also returns reward tokens that tell us the probability of getting a reward of an expected reward of 1 by the end of the current episode at any current time step. And also, we do not give the model any initial returns to go by any means. It has to learn the initial distribution of the rewards to go by itself. So as we can see in the figure on the left here, the model changes the predicted probability of getting a reward at the end based on the actions that it does as it's progressing through the episode. So as you can see by the blue part here, when the model doesn't do or the action of picking up the key, the probability of getting a reward at the end falls up to less than 20%. However, when the model actually takes the key in the first phase, the probability of getting a reward at the end jumps to 50%, and it stays like that throughout the second phase. And in the last phase, when the model actually reaches the door, the probability of getting a reward jumps to 100%. However, if they do not reach the door, the probability falls to 0%. And as you can see here in the figure on the right, this shows how much attention does the model give to different actions. And as you can see, the model is capable of giving very high attention values to the most important actions done, which are picking up the key and reaching the door. Another interesting aspect to assess is that whether the decision transformers require dense rewards that are available in every step across the trajectory, or are they able to work with sparse rewards. So the way the authors assess that is by changing the D4RL benchmark to have only delayed returns, and they do not give any reward throughout the trajectory, but instead give a final cumulative reward at the final step. So as you can see from the results, the percentage BCA is not affected since it's already reward agnostic. However, when it comes to the CQL, it's severely affected and it's performing much poorly than when using dense rewards. However, when it comes to the DT algorithm, we can see that it's mostly unaffected by such a change, and it maintains a good performance even in such a very challenging sparse reward setting. There are some extra observations regarding the decision transformer network, which is that we require no policy regularization or value pessimism. This is mainly due to the fact that the DT doesn't use any network to explicitly express the value function. And in temporal difference methods, inaccuracies in the approximation of such value function can be exploited and leads to inaccuracies in the policy improvement, which is not the case here in the decision transformer. Additionally, you can see that the decision transformer can actually be beneficial for sample-efficient online regimes by basically leading to a much more effective initial policy learning from the available demonstrations, which is usually followed by a refinement step through the interaction with the environment. Lastly, you can also see that the decision transformer can act as a strong model for behavior generation in general. So to conclude, we have so far presented the decision transformer architecture, which is an effective model-free supervised offline RL algorithm that uses sequence modeling to solve RL problems, however with no reliance on any of the traditional RL concepts, and borrows some of the main concepts from the upside-down RL field to not only give us and solve the credit assignment and distribution shift problems that were previously seen, but it also matches or even at some points surpass the offline model-free RL state-of-the-art methods. Some possible future directions for research could be trying out larger transformer models available in the literature. Could also condition on return distributions rather than discrete returns to go, which is similar to what is done in distributional RL to account for stochastic settings. We can also model the evolution of the states and the state dynamics using the transformer model to be an alternative for model-based RL methods. And lastly, we need to understand, and more research needs to be put in understanding the errors made by the transformers for risks in the deployment of such methods in real-world settings. There is a set of limitations that could be worth looking into for the decision transformer architecture. To begin with, we can see that there is a very high dependency on the context length in order to solve the credit assignment problem effectively. To be specific, for the key-to-door environment that we saw previously, the authors had to set the context length to be equal to the full trajectory length in order to successfully do the credit assignment in this task. In general, this will constrain us to always look for the best context length for each task to be able to properly assign the delayed rewards to the correct actions. Another problem is that the authors didn't include any comparison for the computational time of the DT method compared to the other baselines. And also the scalability of this architecture needs to be further analyzed. Moreover, for each task that we use with this model, prior knowledge on the maximum rewards for the tasks will need to be known in advance, and such prior knowledge may not exist for some of these tasks. Lastly, we said previously that this method no longer uses any of the traditional RL concepts such as Bellman backups, temporal difference, even discounting. This leads to the loss of the theoretical guarantees such as convergence guarantees, for example, that were associated with those concepts previously. Here are the references. Thank you so much for your time, and please feel free to check the original paper for more information.